A system generates a 60-bit encryption key. That means there are exactly 2 to the power of 60 total possible keys. But the system rejects any key that is just a shorter sequence repeated multiple times. For example, a 12-bit sequence repeated 5 times, or a 2-bit sequence repeated 30 times. We need to find exactly how many perfectly strong keys are left. A direct method is to take the total 2 to the power of 60 and subtract the weak keys. The repetitions occur at divisors of 60, so we subtract the sequences that repeat every 30 bits, 20 bits, and 15 bits. But here is the problem. A key that just repeats 0 and 1 every 2 bits is in the 30-bit overlap, the 20-bit overlap, and the 10-bit overlap. We just subtracted it multiple times. To correct this, we add the intersections back, then subtract the triple intersections. This requires calculating a 12-set inclusion-exclusion. It is inefficient to compute this way. Instead of calculating the total and subtracting, we define the terms constructively. Let S of n be the number of perfectly strong keys of length n. Every 60-bit key in existence is formed by taking exactly one strong key of some length d and repeating it until it hits 60 bits. This means if we add up all the strong keys for every divisor d of 60, they must exactly equal the total number of 60-bit keys. We get this exact equation, 2 to the power of 60 equals the sum of S of d for all divisors of 60. We want to evaluate S of 60, but it is one term within this summation, along with S of 30, S of 20, and the others. To solve for it, we apply the Möbius Inversion Formula. If you have a total sum f of n defined over divisors, you can invert it to solve for f of n. We use the Möbius function, denoted by mu of n. This function systematically evaluates the inclusion-exclusion coefficients. The function has 3 simple rules. First, mu of 1 is exactly 1. Second, if n has a squared prime factor, like 4, 9, or 12, the function evaluates to 0. This eliminates those divisors from the summation. Third, if n is a product of distinct primes, the output is -1 to the power of k, where k is the number of prime factors. Let's apply this to our equation to isolate S of 60. We list the divisors of 60. According to the second rule, any divisor containing a squared prime, like 4, gives a coefficient of 0. We remove them from the calculation. For the rest, we plug them into the formula. When d is 1, mu of 1 is 1, so we have positive 1 times 2 to the power of 60. When d is a single prime like 2, 3, or 5, mu is -1, so we subtract 2 to the 30th, 2 to the 20th, and 2 to the 12th. For products of 2 distinct primes, like 6, 10, and 15, mu is +1. We add 2 to the 10th, 2 to the 6th, and 2 to the 4th. Finally, 30 is a product of 3 primes, so mu of 30 is -1, meaning we subtract 2 squared. This evaluates the exact number of perfectly strong 60-bit keys. The Möbius inversion formula provides a direct algebraic method instead of a complex inclusion-exclusion computation. If you found this useful, make sure to like and subscribe to Mathilda Academy.